So after all this beautiful data has been generated, why would we do more? Why would we go after yet another fraction of this material? Well, during my PhD research at Queen's, I did some work in the Flin-Flon area, and the most robust numbers that I could get out of till, and these tills were on top of carbonates, on top of VMS deposits. But the most robust signal I could get geochemically was from that ultra-fine, the clay fraction, the 2-micron fraction. So we've already seen that we have beautiful data. Can we get even better data out of it? That was really the premise of the study. And then, of course, by doing that, we need to spend a little bit of extra money to get the clays out. Is it worth doing that? That's the central question. So I have to acknowledge a few people. 3 of the 4 are sitting here on stage. So thanks to Ray Lett, who actually helped me retrieve about half of the samples from the BCGS archives in Victoria. And both Wayne and Dave for doing excellent work in collecting the right sample and treating it properly and collecting enough for me to go then after to do more with that sample and still have some left over for archiving. So that's phenomenal work. And lastly, I should acknowledge Jamil Seder at BV Minerals, formerly Acme, who cut us a deal. So for the purpose of public geoscience, he gave us a good rate on the lab analysis. So you've already seen this. So of the 2013 and 14 campaigns, I was able to actually extract 1,222, almost all of them, samples that were collected by Wayne and Dave. I tried to go after the older GSC archived samples as well, but after the reanalysis that they did in 2015, we actually ran down to such little sample that they said, no, we're gonna keep those archived. So I didn't have access to that, but still a very a beautiful spatial coverage of the area and enough material for me to actually really work with. So clay separation is a wet process. So the 63 micron fraction that we were looking at earlier, that is really as fine as it is practical to sieve dry material out of a till sample. It takes a while and you don't get very much material. So to go down to clay fraction, actually less than 2 micron, you need to suspend it in water and spin it out. So you first spin out the coarse material, and then you're left with the suspension of the clays, and you spin that out at high speed, and that material you then analyze by Acarija. So I'll compare those 2 fractions, and we'll look at the benefits of the clay extraction and see if they're actually worth it. So bear with me, the first couple of slides are going to be QA/QC, so stuff that people always want to skip. But luckily, Dave already explained the probability plots to you, so you can all see what's good data and what's not so good data. I helped you by highlighting the ones that are really quite useless in red. So this is 53 elements, right? I mean, this is ICP-MS high quality data. So you can see for some of the elements, there's just not enough to actually do something with. I mean, some of these, the PGEs, you might still plot as individual maps to see if something pops out, but you definitely don't want to do any multivariate analysis on that. Apart from that, most of these elements, 42 of them, actually produce really good data. And I was also lucky that Wayne actually found some samples in his storage that allowed me to take duplicates and actually do duplicate analysis. So I did that to actually get a handle on the precision. How good, how reproducible is this clay sample or this clay number that I get from the lab? So I submitted those. So these include both the field imprecision, because they are different character splits of the same sample, so they're not identical, and include, of course, the laboratory precision as well. So I used 64 of them. Here's a reference line, y is x, and so this is all the clay fraction, right? So these are just duplicate pairs of the clay fraction. And you can see that just from looking at these XY plots, that it's already really good reproducibility where we have proper data. Now we can take that and one step further, and rather than looking at a plot and saying yes or no, this is good or bad, we can actually put a number on that. We call that the coefficient of variation. That is just a measure. It's also known as the relative standard deviation. So that gives us a number of, put a number on the reproducibility. So anything under 10% is really good. Most commercial laboratories, especially for soils, will not guarantee much beyond that in terms of their lab reproducibility. So for us to have field duplicates that reproduce like this is very, very good. Generally, we in the geochemical world are happy to accept up to about 20% for field duplicates of this kind of material. So the fact that most of our elements are well below that shows us that even when we go through the process of taking separate samples and taking the clays out of those separate samples, we still get very good reproducibility. So of course for things like, well, zirconium is an element that, primarily sits in zircon. It's not very well dissolved by acaricea, so we don't need to worry about that too much. And then antimony and gold are just such low numbers that we're really, pushing the boundary on what we can detect there. So overall, very good, very reproducible data. We also, of course, did the CRM work and showed that there was no significant drift in the lab. So good numbers. So that said, now we're happy that those clay numbers are indeed good on their own. How do they compare to the coarser fraction, right? That 63 micron fraction that was just presented by Dave. So here are split probability plots. It's just the variation on the former probability plot where the clay fraction is in purple and the coarser fraction, 63 micron fraction in orange. And you can see the difference, and you can see that generally there's that the numbers, the actual content of the clay fraction are much higher. So these are all log scales, as Dave already explained. I don't need to explain that to you. So on average, they're like up to about two to three times the number that you would get out of that coarser fraction. And there's a number of reasons for that actually. So I'll show you in a little bit. That has to do not only with the finer fraction having the clays being better at absorbing, positive ions to its negative surface, but also because it's so much finer, it is actually more susceptible to attack by acid. So when we expose it to the same process of acaricea digest, we actually dissolve more of that sample. So fine, so we get higher numbers. What's the next benefit? Well, with those higher numbers, as Dave also explained, I'm a little bit hesitant to apply the regression technique to predict what's going on below, mostly because I want to see where do the numbers plot that I have a lot of confidence in. But when you look at gold and the gold distribution, so not only are the absolute numbers higher, they're about double. The 2.2 is the ratio of the medians there. So not only do we get higher numbers, we get also more precise numbers because of that, right? So we're in a better position, so we have more confidence in the data. So you can see that there's a significant improvement in data quality, not just in gold content. And when we then look at the different maps, we do see that some things just pop out, even in the coarse fraction. Of course, we see Capoose and the 3 T's. Blackwater, not so much. It's a pretty, subdued anomaly. And around the Chu area that Dave already pointed out, it really stands out. I'm using a gridding parameters here with a 500 meter cell size, so the average distance being 2 kilometers, or between the samples. We don't want to really go finer than about a quarter of that. So when we look at that, we do see a number of hotspots that disappear in the 2 micron fraction, where we have higher numbers and better confidence in our data. So those are, in my opinion, likely, unless you have supporting evidence, going to be false positives in the coarser fraction. So be careful with that. But more importantly, perhaps, is where we do see anomalies in the clay fraction that we don't see in that coarser fraction. So those are the false negatives, assuming, of course, that that the numbers in the clay fraction are indeed more reliable. But what we do see is that we also get more of a spatial continuity. We get more of a trend in the anomalies that we see in the clay fraction. So it also gives us more confidence that it's not just this single point anomaly that we're following up. This is actually, over an area. And I'll show you in a little bit how we can then, this is just looking at a single variable, obviously, but how we can combine that with other elements as well. So, of course, not all elements behave the same way. Here's a little table giving you an enhancement factor. How much more, on average, and the average being the median in this case, so not the actual metric of the... So we're using the 50th percentile and the ratio between the clay fraction and the coarse fraction. So what we see is that mercury has an enhancement of about 3.3. So there's about 3.3 times as much mercury in the clay fraction as there is in the coarser fraction. And you see that there's only a couple of elements down there that are at or below, and those are, titanium, phosphorus, niobium. Oh, now I'm being cut short. Thanks, Ray. Yeah, so we see that there's some interesting elements that we might want to use for whether it's porphyry, epithermal, gold, copper deposits, moly. Well, molybdenum itself is actually not that much enriched. It's just like a factor of 1.2. But the others up there are really interesting pathfinders, I think. So I marked those red. The blue ones are the ones that are inherently enriched in the clay fraction because they are clay components. These make up clays, right? So we have aluminum, of course, and then potassium. Scandium replacing aluminum, trivalent, rubidium replacing potassium, as does lithium, cesium. Gallium being trivalent as well could also substitute for aluminum. So those in blue are highlighted are really the clay, the clay mineral components. Now, so there's already two benefits. One of them is higher numbers, the other one is better precision. Here's another one. When we actually do a little bit of data processing on the major elements and we look for mineralogical homogeneity. Why would you do that? It is Acarrhea data, it's not total, so you can't really put hard numbers on it. That's true, but we can still see trends that are really meaningful. So what I did here, I made molar ratios of iron magnesium over aluminum on the y-axis here and calcium over aluminum on the x-axis, and what we see is that there is a pretty homogeneous background composition that is pretty similar in the two fractions, right? So we're still looking at those two fractions in the two colors. But what we also see is that there, apart from that background clay composition, that's highlighted, the circles there are the 90th percentile contour. So the purple circle is pretty tight. It's a tight cluster and there's not a lot of deviation. In the orange cluster, what we see, there are diversions in the direction of the mafic minerals, so the iron, ferromagnesium minerals and calcium minerals, such as calcite or calcsilicates. The point is that there is a component of that coarser fraction that is not clay. And because it's there, it may influence the absolute numbers of the elements that we're actually looking at, that we're displaying on the map. From my previous research, I know that, for instance, if you have more calcium, you also get more zinc, just because zinc likes to be in carbonate fraction. So if I have more carbonates and if I have more mafic silicates, then my sample, my sample's more influenced by those primary minerals. Whereas if I look at the clay fraction itself, I have a more homogeneous background, which gives me a better chance of actually identifying things that have moved around in a hydromorphic fashion. That one you can ignore, except those numbers are really low, showing that, yes, significant weathering has taken place, despite what those guys will tell you. So yes, it's a derivative. It still has been weathered. Then this is also why the PCAs don't work for Dave. They wouldn't work very well here either, is because there is just not a lot of correlation. But let's look at some gold pathfinders. Let's see if they actually correlate. Let's look at those, you know, the plots, the XY plots, and see what we can use and what not. So there's some reasonable correlation in silver, arsenic, and antimony with gold. Mercury maybe, but yeah, gold and molybdenum not so much. So we can still use this. We don't have to do a PCA. We can just plot all three of them on the map together. And when we do that, we get like a pretty honest representation of what's there and what's there in combination. And you can pick any three components to put on a map like that. So RGB composites are red, green, blue. They're like your TV. So what you do is you put the gold grades in red and arsenic in green and silver in blue. And when they're all high, you'll get a white color. When they're all low, it'll be dark. So you can see here in one map the distribution of those three elements, and most importantly, their combined distribution. So now we see that area around 2 light up like a sore thumb. Also black water pops right out, Capoose and 3Ts all stand out just where you expect them. And then there's a couple of other unidentified areas, one right by NASCO. The star is actually the NASCO pit, which is just an aggregate pit. It's not mineralized at all, but by the town of NASCO. I wonder if this is the metropolis of NASCO doing lots of interesting activities with minerals. Not that I'm aware of. And there's a couple of other spots that are brought out by doing this exercise. And I did do a similar exercise for copper. You see poor correlations generally with copper. But let's have a look at when we just plot those elements, unabated together on a map. Neat thing is that, again, that central area sticks out. Sure, we know that. We know there's molybdenum in the ground. What I am curious about is the till also thinner there? Is there more? Are we closer to bedrock, or is it just a really hot area?
It's much thicker.
It's much thicker. Yeah. Ah, interesting. Anyway, so what exactly is bringing that really large multi-element anomaly about? That's up to you guys to figure out. The really neat thing I find in this particular map is that even though copper and molybdenum don't correlate very well, if you look at that blue area to the northwest, that is really molybdenum rich. And when we move further north, where do we get close to? Andako. So Andako being a hot moly anomaly, in this map too, right? So we're really in elephant country. We can see that on this map, and you can also see, the supporting evidence of the other elements doing that. So with that, I'll just sum up. So we get a higher trace element content in this fine fraction. We get greater data precision. There's enhanced anomaly to background contrast. And because of that more homogeneous mineralogical background composition, we then get improved detection of that potential hydromorphous component. So that stuff that's moved up faults and into our tills. So with that, I'd like to leave the conclusion on the screen. Thank you. Thank you.
Questions? And if you're going to raise a question, can you use one of the microphones, which I believe are being... Questions? Peter.
Yeah, my question's fairly simple. If you have a till anomaly, one that you like the look of, how do you follow up on it? Do you just back a rab drill up and start drilling up ice, or up the direction of ice movement?
So the question being, how do you follow up an till anomaly? Well, in our regional data set, because these are about 2 kilometer spacings, you really probably want to do a little bit more sampling before you start throwing a drill in the ground to hone in a little bit on it. But you're right, you do need to go up ice and you need to identify a little bit of that transport history in order to really hone in on that anomaly before you drill on it. Is that kind of what you were looking for?
Yes, but I guess. Yes, but your till sample's on surface, and so you've got a thickness of till that you need to work your way back to. I know when we were following up till samples in Quebec looking for gold, we would drill up ice, but also collect a sample down the whole drill hole.
Yeah, well, exactly. That's what you want to do. So if you remember that sort of optimized dispersion model, as you move up through the till column, basically you want to be able to trace that back down. So like you said, if you're putting drill holes in there and you're collecting 3D profile samples along that transect, you're going to be able to, theoretically, if you're in subglacial till, trace that back down until it gets to a source. Yeah, so exactly what you said.
Thank you.
I'd like to just add to that I do like the idea of the RAB drill to just punch shallow holes into the overburden and collect a decent sample.
Actually, I've got a question for Pim. When you were looking at the clay-sized mercury data, did you notice any linear trends, anything that would come out?
Yes.
Good, okay.
Actually, yeah, it's too bad that we didn't have more time. But there is a very clear mercury and actually accompanied by a little bit of thallium even, anomaly running along the Tatuk lineament fault zone or shear zone. So that runs all the way across that major central, so sort of in a west-northwest direction, and it also goes off along that Natalcus orientation.
Yeah, because we noticed it in the 63 fraction, and I was just intrigued to see if it's even enhanced in the...
It is enhanced. It's
Good.
better, yes. It's stronger in the clay fraction.
Fantastic, okay. Any other questions? Colin.
Okay, I have a question. It's probably for Wayne or Dave. You mentioned, Dave, that you collected rock fragments, like out of the till. But I haven't seen any analysis of correlations of that with geochemistry. Did you do anything with the lithologic samples?
Yeah, so basically we took the lithologic samples. This is probably more a question for Ray because he's the one that had them in his garage and cracked them all open. And so he had them in his garage, he cracked them all open, and he did provide some sort of lithological context. And we haven't actually been able to work with this data to incorporate it into the analysis, but one of the things we want to do is use, verify our bedrock interpretations or tracing it back to bedrock using that information from the lithology that comes from the pebble data. The complicating factor with that is that the pebbles and the smaller, the silt and clay that we're analyzing, the transport difference on those two different sizes is quite a bit different. So just because we have a bunch of pebbles, it doesn't necessarily mean that our the matrix of the sample is from the same area, but it does give us something to correlate to, and that is exactly why we got them, so that you could, potentially use that to help out.
So you haven't done that yet?
Have not done that yet, no.
But all of the information is in the public domain. So
it is.
If anybody wants to look at it and work with it, it's there. Of course, the variable might be is my ability to correctly identify the rock types. And there we have another variable which...
You've got to mitigate that internal variability, Ray.
Any other questions?
What's involved in putting together the field crews to accurately and correctly collect the samples? Do you have to put a skilled geologist on every field crew, or do you just hire a bunch of locals and train them up, or what?
Generally, we had a bunch of field study sessions with a group of individuals we were using to make sure they were all clear. Travis Farabee from the BCGS helped us with that, as well as Dave. Probably one of the biggest advantages is having some very large individuals that can wield some very large and heavy equipment to dig big trenches. So, but also have someone with them. We worked in groups of 2, and so have one individual who definitely understood the complexities of trying to identify the material, but we needed a second person that could actually dig deep holes. So it was a combination.
So is your technical individual normally a geologist?
Preferably a superficial geologist, because we talked about, I mentioned there's a whole bunch of different types of till, and these things aren't always easy to identify. Even looking at the pit, you sometimes have to take into consideration the associated landforms around you. So we did spend a significant amount of time training our crews to be able to identify this stuff properly. And like Wayne said, every group had someone who was competent to do that. And we literally dug thousands of holes. So after the first probably couple of months, these guys were all pretty well trained up to be able to identify that material. But it is something, it's very important that you do collect the right material. So it's an excellent question. It is important that whoever is doing that sampling, there is someone either to train the crews up really well or someone to oversee what's going on.
Okay, I see a question up there. Truman, what does the next generation of regional geochemical sampling for BC look like? What's for the future?
That is an excellent question.
There you go, Wayne.
Sure, I'll address that. I assume they're talking about upgrading existing regional coverages, such as the RGS stream sediment program, or perhaps the lake sediment programs. I'm thinking that probably any second generation sampling would probably incorporate heavy mineral concentrate sampling, which allows for the sampling of larger drainages and getting an accurate understanding of the chemical composition coming out of these drainages. Basically those in excess of 20 square kilometers. Generally the first pass regional survey tended to concentrate on smaller drainages, although a lot of sampling was done, and if you go through the actual database, you'll find that probably 25% of the samples were actually sampled in larger drainages with conventional sediment grab samples. So actually going through with and doing bulk sampling for heavy mineral concentrates would probably be a very useful exercise.
I think
I wish that you'd sampled some of that ablation till at the same time, or in the same general areas, because I'll bet you'd have got the same anomalies. And because you didn't sample it, we don't know.
Well, we do have ablation till samples because we do have the historic data set where we're able to identify those. So when comparing, that is part of the procedure we went through. We looked at, same with everything else, we categorized everything and looked at the distribution, and the ablation till samples didn't match. Some of them were similar. So there is, there's a very fine line between your true ablation till and your subglacial meltout till. And these things can sometimes look similar, and your subglacial meltout tills will have that same transport history and therefore be comparable to the basal till samples. And it's not necessarily that the ablation till samples don't have a useful signature. It's more that they're more difficult to follow up on. So if you have a large data set and it is correlative, then sure, you can use it. But if you have one ablation till sample, you're going to be really hard pressed to figure out where exactly that came from, unless you really understand, a lot of dynamics that when the ice sheet is no longer there, it's very difficult to understand.
one more question, and then we break for lunch. Anybody? Nothing on the screen? Okay, I'd like to thank the three speakers for some excellent talks and some very stimulating information.